Good morning, children. Today we will continue the revision of the chapter Current Electricity. You are now aware that resistances can be combined lengthwise or we can put them in parallel. This is the connection in series, connection of the resistances in series, and this one is the connection of the resistances in parallel. So, in a series combination, the resistances are connected end to end consecutively, but when we connect two or more resistance between the same 2 points, this is the first point and this is the second point, then they are said to be parallel to each other. There are certain important points that must be discussed for better understanding of the topic. In the first picture, there are three resistances that are connected in series. There is a cell of potential difference V and therefore a current I flows in this direction. This current I flows across R1, R2 as well as R3. Same amount of current. This you have been told earlier in the previous video. Now, when we apply Ohm's law, we will find that the voltage V1 which is set up across R1, V2 which is set up across R2 and V3 which is set up across R3 can be found by using Ohm's law. V1 will be equal to IR1, V2 will be equal to IR2 and V3 will be equal to IR3 and the overall voltage will be equal to V1 plus V2 plus V3. And on putting their values in the Ohm's law to find the value of equivalent resistance, you will find that the equivalent resistance is the sum of all the individual resistances present in the circuit. So this particular combination increases the value of equivalent resistance. That means the equivalent resistance is always greater than the sum of all the resistances. Now comes the resistances in parallel. As observed in the diagram, that the current I now divides into three, I1, I2 and I3, but the total current I will be equal to I1 plus I2 plus I3. So again on applying Ohm's law over here and substituting the values of I in this equation, we will find that the equivalent resistance is equal to 1 upon equivalent resistance is equal to the sum of the reciprocals of individual resistances, and this makes the equivalent resistance of the parallel circuit lesser than the individual resistances. One more thing, in a parallel combination, we find that the same voltage is applied across all the three resistances. Unlike in a series combination where voltage distribution takes place, in parallel combination, voltage V is across R1, across R2 as well as across R3. In parallel combination, current distribution takes place. Hence, parallel combination is always, or you may say generally, preferred over series combination because of these two reasons. First being, the voltage across every resistance or every conductor remains the same, and secondly, the equivalent resistance is less than the value of individual resistances. The next topic is EMF, which is the short form of electromotive force. When no current is drawn from a cell, that is when the cell is in open circuit, then the potential difference set up across the terminals of a cell is called EMF. In this particular picture, you have been shown an electric cell and there are two electrodes placed in the electrolyte. The electrolyte dissociated into anions and cations. These ions move towards the electrodes, because of which a difference in the number of electrons arise between the two electrodes of the cell. Cathode becomes more negatively charged while anode becomes more positively charged. This difference in the electric potential of the two electrodes is called EMF. Here open circuit, we define EMF in the open circuit means what? It means that there is no resistance, no load, no appliance connected to this EMF, right? So this is the concept of EMF. The potential difference that exists between the two electrodes in the open circuit. There are two factors on which EMF depends. EMF of a cell depends. First is the material of the electrode and the nature of the electrolyte. And apart from these two, there are no other factors on which EMF depends upon. There is a term used here which is written R internal or internal resistance. I will come to this particular topic in a while. This is a slide which is explaining the difference between terminal voltage and EMF. As it has been told that EMF is the potential difference across the cell or a battery when the circuit is open. That means in this situation there is no load attached to the cell. So right now if I want to measure the potential difference across its two terminals, the value will be called EMF. On the other hand, when the circuit is closed, that means now I have put a resistor or a load, in this case it is a bulb. Now as soon as I attach the bulb or the resistor here, the circuit is closed, then this bulb will draw certain amount of current and therefore there is some potential difference across the two ends of this particular cell. This potential difference is now termed as terminal voltage. It has been found that the value of EMF is always greater than the value of terminal voltage. Terminal voltage of a cell depends upon the amount of current drawn from it. In the second picture over here, this one describes how to measure EMF and this one describes how to measure the voltage or terminal voltage. So when you measure EMF, you are only concentrating on the cell or the battery, and the circuit should be open. On the other hand, when you are measuring voltage or potential difference, then you measure the potential difference of the external resistor when the circuit is closed. Now children, I have come back to this particular slide. This particular slide, as I have already told you, tells you something very important, which is internal resistance. So just remember that slide, children. However, in this particular slide, which is dealing about electromotive force and internal resistance, the ideal definition of electromotive force is mentioned here. Along with that, there is one expression also for calculation of electromotive force. And in this expression, I have introduced the term small r. This small r is known as internal resistance. When the cell is in the closed circuit, as shown in this figure, as well as here, as well as in the third picture. In all the three pictures, you can see very well that the cell is connected with the external resistance. That means there is a load. So what happens now? Right now, the current will start flowing across the cell. That means the current will now flow from anode to cathode, mentioned over here. And while now this anode to cathode, it will flow inside the cell, but anode to cathode, it will flow outside the cell, but from cathode to anode, it will flow inside the cell through the electrolyte. This is what I am talking about here right now, that the current that flows from anode to cathode within the electrolyte. And why is this happening? Just to maintain a continuous flow, this gives rise to internal resistance. Because when it happens, the resistance is offered by the electrolyte inside the cell to the flow of electrons. And therefore, this is the cause of internal resistance. As mentioned earlier, that voltage drop will be observed whenever the circuit is closed and the current is drawn. And this voltage drop occurs due to the resistance, internal resistance. So here the expression of EMF you write in this way. On opening the brackets, you get this, where IR is the terminal voltage and small this particular factor IR is the voltage drop. So that means EMF is equal to sum of terminal voltage and voltage drop. So this particular expression clearly depicts that in order to find voltage drop, you subtract EMF and terminal voltage. That is the main idea. Next comes the factors that affect internal resistance. There are 4 factors. First is surface area. The greater the surface area, the lesser will be the internal resistance. The greater the distance between the electrodes, the more will be the internal resistance. the more the ionic nature of the electrolyte. More ionic means less concentration of electrons. So, more the electrolyte is ionic, the lesser will be the internal resistance. And finally, the greater the temperature, rise in temperature, the lesser will be the internal resistance. So, these are the factors which affect internal resistance. However, change in temperature affects external resistance also. This you have been told in or while studying Ohm's law. So, the change in temperature affects the resistance of metals, semiconductors, etc. On increasing the temperature, resistance of all pure metals increases, while the resistances of semiconductor decreases. But if you decrease the resistance of temperature of mercury, its resistance will definitely decrease, but at a temperature nearly equal to 4 Kelvin, which is almost minus 269 degrees Celsius, the electrical resistance of mercury metal disappears completely. The phenomenon of loss of electrical resistance by a substance on cooling it to an extremely low temperature is known as superconductivity, and the substances are called superconductors. However, it is difficult to achieve such extremely low temperature, so practical use of superconductors is not possible so far. However, one of the last point which is written over here, I would like to read this sentence, that an electric current through a loop of superconducting wire can persist indefinitely with no power source. But as I have said just now, that maintaining such a low temperature, achieving and maintaining such a low temperature is not possible. That is why this advantage we are not able to get so far. When an electric current flows through a conductor, the electrical energy is used up, and we say that the current is doing some work, and the rate of doing work, electrical work, is known as electrical power. The SI unit of electrical energy is joule, and the electrical power is measured in watts. Please ignore here kilowatt hour, this is incorrect. Kilowatt hour is the unit of electrical energy, commercial unit of electrical energy. So this has been written over here by mistake. Then comes the formula for electrical energy and electrical power. The first formula that we obtained for electrical energy is VIT, where V is the voltage, I is the current, and T is the time. Correspondingly, the formula for electrical power is VI. Second formula for electrical energy is I square RT, and corresponding the value of or the expression for electrical power is I square R. And the last one equals to V square T upon R, and here it should be V square upon R. I am sorry children, it should be V square upon R is equal to power. Okay, so these are the expressions for electrical energy and electrical power. Every electrical appliance like a bulb, fan, etc. has a label or engraved plate on it. You must have seen. And these engraved plates or labels tells us the voltage which needs to be applied and the electrical power consumed by it. It therefore tells us the rate at which electrical energy is consumed by the appliance. For example, if a bulb is rated 240 volt and 100 watt, it means that this bulb is to be used on a voltage of 240 volts and 100 watt. In other words, it has power consumption of 100 watt, or we can say that it will consume electrical energy at the rate of 100 joules per second. Now there is one important point which is written here, which says that if you connect it across a lower voltage, then its power will be less than 100 watt and it will be dimmer. And if you connect it across a higher voltage, then its power will be more than 100 watt and it will be brighter. This is our last slide, which tells us about heating effect of current. When an electric current is passed through a high resistance wire like nichrome wire, the resistance wire becomes very hot and produces heat. This is known as heating effect of current. It is obtained by transformation of electrical energy into heat energy. Heat produced is given by the formula H is equal to I square RT, which clearly says that H is directly proportional to I square. That means if you double the current, heat generated will become 4 times. H is directly proportional to R, which means if you double the resistance, it will double the heat produced. And finally, H is also directly proportional to time for which the current is passed through the conductor. Out of the three, current has more impact on heat as compared to resistance and time. Now there are numerous applications of heating effect of current. These are in iron, electric heater, water heater, room heaters, bulb, electric fuse, etc. Thank you.